Math 1332, Chapter 2, Set Theory, Section 2.1, Introduction to Set Theory, Video 8, One-to-One Correspondence, Equal and Equivalent Sets. This is the last video in the series for Section 2.1, but the topics that we're discussing we are going to build upon through this chapter. Once we leave Chapter 2, then we can kind of put these things in the back burner. But if you pay close attention when we move to Chapter 3, you'll see some connections between Chapter 3 and Chapter 2. But let's wrap up this section. Let's start by defining what we mean by one-to-one correspondence. And I've already got the definition here, right here. Let A and B be two sets. Then A and B can be put in one-to-one correspondence if you can pair each element of one set with exactly one element of the other set. You already have the idea of what it means to be able to put two sets into one-to-one correspondence. In fact, even infants and toddlers have this idea. Now, what do I mean by that? Well, assuming that you have 5 fingers on your left hand and 5 fingers on your right hand, have you ever done this? Paired up your pinkies, your ring fingers, your middle fingers, your pointers, and your thumbs to do something like this. If you have, then you have put your fingers on your left hand in one-to-one correspondence with your fingers on your right hand, because for every finger on the left hand, you pair it up with exactly one finger on the right hand and vice versa, and there are no fingers left over. Now, let's say that you had a tragic woodworking accident or something, and you lost your thumb, so that you only have 4 fingers on this hand. Could you now put your fingers on your left hand in one-to-one correspondence with the fingers on your right hand? And the answer is no, because if you were to pair up one-to-one, one on the left, one on the right, then you would have one guy left over who does not have somebody to pair with. In order to be a one-to-one correspondence, everybody has to have exactly one element to pair with from the other set. Now, if you're asked, can you put two sets in one-to-one correspondence? And you'll have to forgive me, I didn't actually ask a question here. So let's go in here and put a question real quick. Can the following pairs of sets be put in one-to-one correspondence? All right. So let's start with the ones on the left. I know it's not a big deal, but it's going to bother me. There we go. All right, let's start with the sets on the left. The set A contains the elements 1, 2, 3, 4, and 5, and the set B contains the elements A, B, C, D, and E. Can we put these in one-to-one correspondence? In other words, can we pair them up? And it should be pretty obvious that the answer is yes. One possible correspondence is to pair up the number 1 with the letter A, the number 2 with the letter B, the number 3 with the letter C, the number 4 with the letter D, and the number 5 with the letter E. Every element in A is paired up with exactly one element in B and vice versa. Nobody's left over, nobody's paired with more than one. So the answer to this one is yes. Now, it is worth pointing out that when you put these in one-to-one correspondence, you don't have to put them in what would seem like the most natural correspondence. For example, maybe I pair 1 with the letter B, 2 with the letter A, 3 with the letter E, 4 with the letter C, and 5 with the letter D. Why? Why not? But that's still a one-to-one correspondence because every element in A is paired up with exactly one element in B and vice versa. As long as a one-to-one correspondence exists, that's all that matters. Let's look at the second example. Set A still contains the numbers 1, 2, 3, 4, and 5, but set B contains the words red, blue, and yellow. Can you put these in one-to-one correspondence? And it should be pretty obvious that the answer is no. You cannot. If you tried, here's what would happen. Pick somebody to pair with the number 1. Let's say the word red. Now pick somebody from set B to pair with the number 2. We'll say yellow. Why? Why not? Now let's pick somebody to pair with the number 3. Well, the only one left is blue. I can't put these in one-to-one correspondence because one of two things will happen. Number one, somebody's not going to be paired up, in this case 4 and 5. But if you tried to pair up 4 and 5, we're going to run into a different problem. Let's say 4 goes with red and 5 goes with yellow. Now you have the problem down here. The word red is not from set A. Sorry, I accidentally unplugged my headset there, so let me say that again. If we were to try to pair everybody in set A with somebody in set B, then we fixed the problem with A. Everybody in A only has one thing it's paired with, but we created a problem in B. The word red no longer has one number paired with it, it has 2. For a 1-to-1 correspondence, you can only have 1 paired with 1, not 1 paired with 2. And the same thing with yellow. In this case, yellow is paired with both 2 and 5. That's not 1-to-1, that's 1-to-2. So no matter how you try to fix the problem, either by giving everybody in the first set somebody to pair with, either by keeping it 1-to-1 and 4 and 5 in the first set not having a partner, or forcing everybody to have a partner, and in set B somebody has more than one partner, it's always going to break the condition for being 1-to-1. So I cannot put a 1-to-1 correspondence on that particular set. All right, so that's the concept of a 1-to-1 correspondence. Can you match up everybody so that everybody has exactly one partner and nobody is left out like this poor thumb? All right, so let's talk about what it means to be equal and equivalent sets, starting with equal sets. 2 sets are equal. 2 sets are equal if they have the exact same elements. It's exactly what you think it would mean. These sets are exactly the same. So we have 3 pairs of sets here, and we're going to answer the question, are the following pairs of sets equal? In example A, we have set A equals a set of x's, such that x is a natural number and x is less than 4. And B is the set containing the numbers 3, 2, and 1. Now, in order to see if these are equal, we need to see what their elements are. And if they're exactly the same, then the sets are equal. We already know what set B contains because it's written in roster method. Set A is written using set builder notation, so we need to figure out what's in A. I need the natural numbers, and they have to be less than 4. Natural numbers start with 1, and I want all of them as long as they're less than 4, so I have to stop at 3. Do A and B contain the exact same elements? Yes, they both contain 1, they both contain 2, they both contain 3, and that's it. Therefore, A and B are equal. And if you're wondering, can we just write an equal sign between them? Yes. But that's what it means for 2 sets to be equal if they have the exact same elements. There is a more rigorous definition, but we're not ready for it yet. All right, example B. Set A, the letters in the word stop. Set B, the letters in the word scoop. Now this will actually bring up something that I haven't discussed yet, so pay close attention. Both of these are written using the descriptive method, but since we're seeing if the elements are the same, let's list their elements. Set A contains the letters in the word stop, which clearly are the letters S-T-O-P. Set B contains the letters in the word scoop, which is the letters S, C, O, and P. And the issue we haven't talked about before is whether or not we should repeat an element. Clearly in the word scoop there are 2 O's, but should I list it more than once? Should I list it twice when I'm listing the set in roster form? And the answer is no. Because when you have a collection of objects, all you want to know is who belongs to the set. You're not necessarily asking how many times it belongs to that set. There is a way to codify a set so that you can represent an element multiple times, but then we start getting into ordered pairs, and then it starts looking a lot like algebra. So in short, we'll just say that when we're listing elements in a set, you do not need to repeat elements. So are these 2 sets equal? Do they have the exact same elements? And the answer is almost. They both have an S, they both have an O, they both have a P, but this is where they're different. All it takes is one bad element. The letter T does not belong to both. That's enough to say that you're not equal. The letter C does not belong to both either. But that also means that they're not equal. So these are not the same sets, and so we would say A is not equal to B. And let's take a look at the third one, example C, N and W. Keep in mind that these are specific letters for specific sets, N being the set of natural numbers, which is what you count with. They're also called the counting numbers. So 1, 2, 3, 4, and they go on forever. W is the whole numbers, which is the natural numbers and the number 0. So we start with 0. Dot, dot, dot. Are these equal? Almost. They have almost the exact same elements, but there's one exception. Who's the one element that makes the sets not equal? 0. 0 belongs to W, but it doesn't belong to N. Therefore, the natural numbers are not equal to the whole numbers. So the concept of set equality is really pretty straightforward. If your elements are exactly the same, your sets are equal. Otherwise, you're not. Well, what does it mean for two sets to be equivalent? Two sets are equivalent if, I'm going to fix that, it's going to bother me. So let's do that again. Two sets are equivalent if they can be put in one-to-one correspondence. Now, if you think about it, one-to-one correspondence pretty much just means that they have the same number of elements. But that's the same as saying that they have the same cardinal number. So there's three ways to think about sets being equivalent. Number one, you can match up their elements in a one-to-one correspondence. Everybody has exactly one partner. Nobody's left over. Nobody's paired up with two partners. But that's the same as saying they have the same number of elements, which is the same as saying that they have the same cardinal number. So there's really three perspectives on how to look at equivalent, either in terms of one-to-one correspondence, same number of elements, or the same cardinal number. Now, if you'll notice and look at these three examples, these are the exact same sets that we had in the previous page. So for example A, set A, set of natural numbers less than 4 is still 1, 2, and 3. Set B was given to us in roster form 3, 2, and 1. If we were to talk about these in terms of cardinality, the cardinality of A is equal to 3. It's got 3 elements. Cardinality of B is equal to 3. And since they have the same cardinal number, oops, I'm sorry, I knew this was going to happen, the 3-dot triangle. I'll go ahead and introduce it to you now, although it's not formally introduced until chapter 3. It's a very common symbol in upper level mathematics, but the 3-dot triangle is a symbol for the word therefore. It usually precedes when you draw a conclusion to something or answer a question. And I will use it without thinking twice like I just did. So I owe it to you to explain that the 3-dot triangle is simply a symbol for the word therefore. I'm going to go ahead and leave it here. Therefore, A and B are equivalent. Is there a symbol for equivalent? There probably is. It probably looks like this. But we're not going to go there because the textbook I'm using doesn't currently use that. But equivalent simply means that in this case, they have the same cardinal number, which is the same as saying that they have the same number of elements. Let's look at example B, where set A contains the letters in the word stop, so it contains S, T, O, and P. And set B contains the letters in the word scoop, and as we already mentioned in the previous example, you do not list an element more than once. Are these equivalent? Yes. You can make a cardinality argument. The cardinality of A is equal to 4. The cardinality of B is equal to 4. You could put them in one-to-one correspondence, match the S with the S, the T with the C, the O with the O, and the P with the P. So there's the one-to-one correspondence. Or you could just say that they both have 4 elements. So yes, they are equivalent as well. And since I introduced the therefore, let's go ahead and keep using it. Therefore, A and B are equivalent. They have the same number of elements. So equality is a stronger condition than equivalence. Equivalence just means you have the same number of elements. Equality says your elements have to be exactly the same. What about the last one, the natural numbers and the whole numbers? I'm going to open up a new page to talk about this one. We're still talking about sets being equivalent. The natural numbers being 1, 2, 3, 4. The whole numbers starting with 0. And remember, we have 3 ways to talk about equivalent. Same number of elements, same cardinality, one-to-one correspondence. But can we really make a cardinality argument here? Well, the cardinality is the number of elements in a set, and both of these sets are infinite. And we really haven't talked about how to describe the cardinality of an infinite set. Kind of casually mentioned is its cardinality infinity, but the discussion is actually a lot deeper than that. So since we can't count the number of elements, and we can't compare cardinalities, maybe we can set up a one-to-one correspondence. Remember, one-to-one correspondence simply means that everybody has a partner, nobody's left out, and everybody has exactly one partner. So can we pair these numbers up? And you might be thinking pair up 1 with 1, 2 with 2, 3 with 3, 4 with 4, etc. No, there's not a one-to-one correspondence because the 0 has nobody. But just because that correspondence wasn't one-to-one doesn't mean a one-to-one correspondence doesn't exist. Because if you ignore the fact that some of the numbers match and just look at where they're positioned, this 1 can be paired with that 0. This 2 can be paired with that 1. This 3 can be paired with that 2. This 4 can be paired with that 3, and we can continue that forever, so to speak. And if we did that, would everybody in the top have exactly one partner on the bottom? Yes. And would everybody on the bottom have exactly one partner on the top? Yes. This is a one-to-one correspondence. We'll just say one-to-one for short. And by the actual definition of sets being equivalent, if you can put them in a one-to-one correspondence, then the sets are equivalent. Therefore, the natural numbers and the whole numbers are equivalent. And this really messes with some people's heads, because how can they be equivalent when every natural number is a whole number, but not vice versa? In other words, if you think about this, every number, getting my highlight ready, every number that's in the natural numbers is also in the whole numbers. So your brain is probably trying to say, but W has more numbers than N because it's got all the numbers from N and a 0. So how could they possibly be equivalent? How can one set be inside of another and still be equivalent? I'll tell you right now, I'm kind of foreshadowing the end of this chapter, but the short answer is because they're both infinitely large. Now be careful. That doesn't mean that 2 infinite sets are always equivalent, but these 2 infinite sets are, because I could put them in one-to-one correspondence. All right, I want to wrap up this video with a couple of true-false statements, which you just saw right here. True or false, if 2 sets are equivalent, then they must be equal. Let that sink in. Let's say you have 2 sets that are equivalent. Must they be equal? Well, we've got an example. That would be the green ones. They were not equal, but they were equivalent. So let's go back to that question. If 2 sets are equivalent, A and B, the green A and B are equivalent, then they must be equal. Were those 2 sets equal? No. So in terms of true or false, this statement is false. 2 sets can be equivalent without being equal. I'll just give a real quick example. A equals the set 1, 2, 3. B equals the set 4, 5, 6. Are they equivalent? Yes, they both have the same number of elements, 3 elements. Are they equal? Clearly not. The set A contains the number 1, the set B does not. Remember, to be equal, the elements have to be exactly the same. What about this last one? If two sets are equal, then they must be equivalent. Well, let's check our examples. The only equal sets that we had here were in the first example, and I'm going to highlight them in a different color. Oops, not what I meant to do. Here we go. Those are the only two sets that we had that were equal. Were they equivalent? They were. Now be careful. One example doesn't mean that that's always true. But I think it's pretty obvious that it must be true. Or at least I think it's obvious. So if two sets are equal, they must be equivalent. That statement is true. If they are equal, they must have the same elements, which means they must have the same number of elements. Because remember, equality talks about having the exact same elements, whereas equivalence only talks about having the same number of elements. So from this, we can say the following. Well, we've already said it. If two sets are equal, then they must be equivalent. That is true. This one, not so true. Best way to keep them sorted out is to have a counterexample to the one that's false. These two sets are equivalent but not equal. Therefore, being equivalent doesn't guarantee being equal, but being equal guarantees being equivalent.